What would be the most sustainable catheter we could design from scratch with today's technology? This was the case study Damian Carr and I set out to solve in this episode. Damian is the founder of Eyedea MedTech Education and the author of the Catheter R&D Handbook. He has 20 years of hands-on catheter design experience and is overall just a brilliant human being and a good friend of mine. In this episode, we are going to tackle the following problem. We're going to be conducting a concrete case study to design the most sustainable guidewire catheter with optimization for cost, environmental footprint, and recyclability. For this, we first have to learn how traditional catheters are manufactured and where the biggest sustainability problems are. Then, we are going to learn about processing innovations like co-extrusion and reel-to-reel manufacturing and how they can eliminate waste and cost. Then we're going to learn about PFAS-free liner materials that can change the game for both materials and process design. I'm Lucas Pinegonda and I've helped over 40 medtech companies to be more sustainable with plastics. This episode was sponsored by Masterflex Group and the link to their homepage is in the description. So without further ado, here's our conversation. Hi Damian, and welcome to the podcast.
Thank you very much, Lucas. Great to be here.
Yes, so I'm super excited for this one because this is the one that I wanted to do for a long time. So the let's say case study that we have laid out together is that we want to take or analyze how catheters are made today and how we could make them with state-of-the-art technology better, more sustainable, more cost-effective, and better for the patient. So this is the case study we're trying to tackle in the next 45 minutes to an hour. So Damian, you might want to explain what a catheter is to the uninitiated, how it is composed, how it is designed, and what it should do.
Perfect. So a catheter is essentially a long, thin, often flexible straw that is used to get from outside of the body to inside of the body. When you're inside there, it's limited to your imagination what we can do with these. There's over 7,500 different applications for catheter technologies in Europe alone. So think long, thin, flexible tube and then put different applications on the end, whether it's a balloon, whether it's a camera, a sensor, a microwave to burn away tissue inside of the body, or something to collect a bit of tissue so we can test it in a lab. So keyhole surgery, minimally invasive surgery, anything along those types of lines.
Okay, perfect. So how is a catheter designed today?
So a catheter is typically designed from a set of user needs. So it'd be user needs and patient needs. So you'll find out what the problem is within the body. Say it's a cancerous tumor growing in the lung. You would then find a technology that could burn or freeze that cancer and kill it. And then you would make the long, thin, flexible straw that will hold that technology on the end and bring it into the body safely. So it's designed often in isolation in a lab from engineers who get these design inputs. And there is a big, massive gap between the clinical use and the engineers actually developing it. But that's something I'm slowly working on the outside.
Perfect. So walk us through the different, let's say, components of a catheter. And to make it simple, the most used catheter is the guidewire catheter. It's the one that is used the most. Walk us through this simple catheter.
So it'd be more of a guiding sheath or an angiograph catheter. It's a simple basic catheter like what I'm holding in my hands here. So one of the main requirements is that it has to be able to bend and travel down the body. So depending on where you're going, you need it flexible on one end and a little bit stiffer where the surgeon will be holding, twisting, torquing, pulling, and pushing. Then on the inside, you want a very lubricious ID, inner diameter. So we often use the likes of PTFE on the inside, which is not the most sustainable in the world, but that just allows you to glide one device inside of another device with like 10% the thickness of a human hair.
Okay, so you have the inner layer, which is usually very lubricious. That is the function that the inner layer has, and it's usually a very typical application of PTFE Teflon, or which is the brand name it's most known for. And then you have, walk us through the other layers. What other layers do you have?
Perfect. So to make this much more easy, I'm going to make it visual and show you step by step the ways that we actually build devices today. So the very first step of building a tri-layer construct, so this is the three main layers that we talk about. This is the traditional way that we still actually often use today for devices that could be under 100 or 2,000 units a year. So the very first step is you need to get your mandrel, and your mandrel is just stainless steel. It's reusable in most cases, fortunately. And first thing you might have to do is clean that. So you get your IPA and your wipe, clean that down, make sure that there's no cuts, no tears, no burrs off it, no sharp edges. Reasonably simple enough, but a bit of a step. You then have to cover over that with your PTFE liner. So this is that PTFE tube that you want to place over. So you get your liner, get your mandrel, slide your mandrel into your liner. Try to touch it as little as possible. Try not to even look at it because the etching on the outside that allows us to stick it is very temperamental and fragile. Would not do well in school getting bullied. But then the next thing you do, if you're putting a liner on, if it's etched, usually you would have to stretch it. And then you'll have to end up tying a couple of knots onto the outside of it. So this just makes sure that it just holds really tight to that mandrel. So what that would look like is this is the knot that you would tie on the end of it. And when you're stretching it, you catch from the center, pull it out to two sides. You try to do this in as few steps as possible. And then you twist the ends. And then you try to create and form a knot as small as possible on the end of one of the devices. Now, this process alone could take someone 2 or 3 months to be able to master before you'd actually trust them with these liners. Otherwise, they could damage that surface, that etched surface that allows us to stick one to the other. Now that we have that done, the journey is just really starting. Next thing we have to do is put essentially a skeleton into the device. And this makes sure that it's very strong, durable, keeps the circular inside circular, stops it ovalizing. And then if some parts of the device breaks, this also is our fishing line to help get the device out. So this goes through a braiding machine. Braiding machines are, as you'll see here, in real speed. The bobbins are spinning fast, the device is moving slow. This could take 10, 15, 20 minutes for one device to go through from one side to the other. Once you have it out the other end, you might need to cut and terminate that braid so that you're not cutting it at the very end and the wires open up and become really sharp points that go into the person. So you would think we have a very advanced, intelligent way of doing that. No, we do not. We put on a little bit of FEP heat shrink. This is just to hold the braid in place, and then we go in under a microscope with a snips and snip each one of those 16 wires, or 32 or 48 wires, and then we tuck them back in with the tweezers. Lovely job. Traumatizes people. I think after 6 months, people will actually walk out and leave a company if they're just left in this process. And then say we want a device like this that might be going deep into the body, so you might have different sections of plastic that you want to put on the outside. So as I said, stiff where you're holding and controlling, soft where it's bending around the body. So you might pick 3 different jackets, ideally of the same material so that you know they stick together, they melt at the same temperature, that they can intertwine and hold on together. Because you have like the thickness of a paper sometimes holding these 3 different materials together, or 2. So first you want to cut them very straight so that at least you know the ends are connecting together. Place them onto your assembly. And then you would place over a heat shrink and melt all these down together. So a heat shrink is like that collar that they put on electrical wires, and then you just put heat on it and it shrinks down to hold everything in place. So your jackets are on, cover it with a heat shrink, and as you see below, that heat shrink is shrinking, it's melting the plastic underneath and letting it turn to a liquid and just attach onto that inner liner, that etch layer that we talked about later. It's kind of like goosebumps and hairs. And then if you are a massive fan of watching paint dry, you will love this process because you just put it under a heat gun or a heat source, or you might have a vertical laminator. You place it in another 10, 15, 20 minutes till it goes through this whole process. It could be going 1 millimeter, 2 millimeters a second. It's not really fast. It's not an exciting process anyways. You then remove off the heat shrink and you have all these layers tied and bonded down together. And this is the same for if you're doing multi-lumen devices. You could just get multiple mandrels. If you don't have a PTFE liner, you'd use a PTFE coated mandrel so that it doesn't stick to that plastic. And then once you have that device done, you could add on things like balloons, like cameras, pull wires inside of it, stints onto the outside of it, depending on what the application, what the therapy or the diagnostic device is trying to do. So simple enough. That is how we are building catheters today.
Yes. So thank you very much, and also thank you very much for putting together these lovely animations. I know that you spend way too much time doing them, but you love to do them. It's you really see the passion that you have for educating people on minimally invasive surgery. So we have laid this out, and what strikes my mind as a, let's say, outsider to the catheter space, it's a very manual and very, let's say, I wouldn't say medieval, because it's a very, very, let's say, high tech device that goes into a body that is a very high regulatory risk, but it's a way of working that you would maybe find in the 19th century, the 18th century manufacture, where you have masters of the craft who have mastered the physical skill of manufacturing something to perfection, but it's not in any way, shape, or form suitable for industrial manufacturing. So, what's your take on this? Am I doing you wrong, or is this
No,
on
that
point?
is unfortunately the reality. Usually it's first generation devices. You give the task to an R&D team. It's an early stage R&D team, so they have limited budget, and they're told you need to build a device to prove this works. They spend 6 months a year, sometimes 2 years, building those first devices to prove it works. And then because the time took so long, their budget was so small, they'd done it in this manual way on a desk in a lab to build them. And then very, very quickly, the team, the company, the organization wants to go into clinical trials.
Mm.
Once you start clinical trials, it can be very difficult to change that process. So it's much easier to just pass that whole process as you were doing it with a cheap budget and a small team, 2 or 3 engineers, a couple of technicians, and that just gets transferred to process development. And then their whole goal is to just improve these processes because they were not there when these processes were selected, why these materials were selected. Their job was, this is how it's done. You just make it better, but don't change anything. So that is the stress and the strain that ends up getting passed down the boat, passed down the river on the boat. And then once you build that device and you've understood and mastered all those processes, you go to your next device and you just try to improve their performance. But the same thing is you could be using very similar processes rather than completely reinventing the wheel and seeing how people would do it if they had never seen these traditional ways of
Yeah,
doing it.
yeah. I mean, that is the first thing that strikes me. The second thing that strikes me is, the heavy use of fluoropolymers. You rely on the PTFE liner, you rely on the heat shrink, you rely on PTFA coated mandrels so that you can remove the devices, which is going to be a regulatory risk at the moment in Europe. So there is the PFAS restriction. It is not finally decided, but it looks very much like that the fluoropolymers are going to get banned. MedTech is going to get some derogation periods, which means that you're going to get more time. But, if we're not starting now to develop these processes to get rid of the fluoropolymers in the future, like how are we going to get there? So this is that. So are there alternatives to fluoropolymers, and how viable are they?
There is, so this push has come on a number of years ago, and in the defense of fluoropolymers, what they have done to transform medtech is remarkable. We would not be able to create, God knows how much of the devices if fluoropolymers weren't around, although maybe necessity the mother of invention, we might have figured out something a little bit sooner. But because of these regulations that are coming in, many companies are working, so the suppliers are working on new alternatives to fluoropolymers. The companies and the manufacturers are experimenting with many of them. There's no pick and place replacement for fluoropolymers. But how the hell should there be? It's not like you are going to go out with a woman, dump her, and expect the very next woman to come on to be exactly like the first one, except work better. That's not how the world works. So if you're working with a new material, it's got new capabilities, new processing temperatures, parameters. You have to look at it in a new way. So there's many new alternatives that are coming out. Some have been out for quite a long while and just not cared about or not used, potentially price, access, familiarity. So they're coming out, but you have to find out what is the fluoropolymer for your, or the fluoropolymer alternative for your application.
I think it really depends on what kind of properties you need. You know, the lubricity is one property. Then the high temperature resistance is another property. The high chemical resistance is another property. And then it being flexible, and then it also being very insulating. If you need all of those properties, you end up with PTFE or with some sort of fluoropolymer. Then you have a problem if you need many of the good quality properties that fluoropolymers actually have. But if you just need one, like the lubricity and the flexibility, you might find something. And you know that this is what you actually need for a catheter liner. And then the heat shrink, you know, if you do a completely different processing method, you would also get rid of the heat shrink. So maybe let's dive into how a ideal future solution could look like in terms of materials, in terms of design, and in terms of processing. What would your ideal Avenger style setup be for the future of catheters?
So I definitely have my own version of an ideal, but if we were to talk about something that a company could start up today, so I wanted to make it realistic, grounded, and not too ethereal. So I will share some slides again and be able to walk through how companies could do it relatively easily. There would be some investments, there would absolutely be development time. If you don't want to engage in that development time, you are in the very wrong industry. So this is a couple of different examples and routes of how you would build an automated tri-layer version of the catheter device that we just spoke about. So the very first thing is, rather than do these one at a time, let's make a kilometer of them. Or let's make 1, 2 kilometers, 500 meters, whatever it may be, depending on what you're actually looking for. So first you get a spool. It could be polymer or it can be silver plated copper. I don't know what would be the most sustainable here. So what I'm going to do is the process and the design, and you can chime in on what the materials would be that would be more sustainable. So ideally you want something that can be taken out the other side and recycled, created back into your spool. And your spool is essentially like a roll of thread. Or a roll of rope. It is just continuous length of it. You could then get an extruder. So this is a beautiful extruder from the likes of US extruders. Shortened down, there's a little bit more to this machine than what you see in front of you. You place this into the back, and then as it comes out the other end, you would end up getting a layer of plastic. One of my favorite materials in the world is ultra high molecular weight polyethylene. I see this as the foundation of a lot of the future PFAS alternative materials. So even the likes of Zeus PFX is based on a polyethylene based. Masterflex are producing the thinnest wall ultramolecular high weight polyethylene that I've seen on the market. DSM are working on these technologies. This is an absolute super material with one little catch like they always tend to have. But you would then place this back onto a spool. So you were going from one machine to another. This is the more easy way. If you had it all advanced, you'd have all this in a straight line. So you take this, and this could be either extruded, or another way you could do it is actually film casting. And film casting is where you get a big bath of the molten polymer. You would place a wire down it, it'll get on a pulley, it'll draw up, cure. If you need to make it a little bit thicker, you could maybe bring it down again, do a second layer of it, bring it down again for a third layer. So you can get very highly controlled wall thicknesses depending on what your application needs. As you move that a little bit further, next thing we have to do is put on the braid. So rather than manually put on the braid, what you could do is you can do reel-to-reel braiding, or continuous braiding it's called. So place your spool in, put it through the braider, turn off the lights, go home, wake up in the morning and realize a wire broke after you walked out the door and you have to fix it and start again. Or in an ideal situation, everything worked perfectly and you end up getting your fully spooled roll out the other end. So now you have a spool that has its liner on it, it has its braid on it, and you can take it in a few different paths. One path you could do is just continuous braiding that goes straight into an extruder, and you do what's called a co-extrusion. So this is just placing a layer down on the outside. This is if we all wanted off the same material. So say we wanted PEBAX 65D the whole way throughout, and then we get our spool of PEBAX 65D with the braid, with the liner, and everything else included. If you wanted to then cut this to length, you put it through an automated cutter. It'll slice it to length. You have sections now off your catheter shaft. You do have issues with those wires potentially open at the end, but there is fixes around that. But another way you could go is if you want to do that braid termination similar to what we were doing previously, there is a series of machines from MSI that levers themselves to this. You have to create the automated hands between it, but you could place a device through that puts on a little bit of PET heat shrink, or else puts on a band or laser welder or some way to connect those wires, cuts off the excess so you have these small little gaps between it. And then if you wanted to go very fancy and you wanted to end up making, this is the section where it might laser weld them around, cut off the end, and you can either cut them to size or leave it on a spool depending on what you're trying to do. And then you could co-extrude onto the outside, but you could do something like dynamic co-extrusion. So there's companies like GMAC who create dynamic co-extruders. So this is if you want to put multiple different jackets onto the same device, and there'll actually be a flow transition between each one of these. And this is the alternative to having to place on each individual jacket. This machine actually just gates on and off different extruders to be able to make those variable durometers. So you could have 72D, 55D, and 35D. That 72 number, 55, that's how hard the material is. So the lower the number, the softer it is. Just for a little bit of reference. And then ways that you can put it on, you can end up overmolding or butt welding on a tip. I'm not a big fan of this process, but I have seen some very innovative ways of melting on lower durometer polymers over the higher durometer polymer so that it's an overlap rather than a connected tip. And then same overmolding on with the proximal end, no glues, no adhesives, no holding them together and waiting for them to dry. And then your catheter shaft is done, and you can connect it on any of the bits at the end, whether it's the balloon or whatever other lumens you're trying to do. So in an ideal world, this would all be a continuous process where you just have machines geared up together that are building out those devices, even if it's like a platform device, and afterwards you shape it or you have different lengths or you create it. And then once we have the manufacturing down, easy step, then we can actually start focusing on building devices that are much safer for the application they're doing. So big problem we have at the moment is we build devices for that target cost of goods that it takes. And these devices work, but just about work after speaking to surgeons and seeing how these devices go wrong. And us engineers working in the silo, not realizing that when we make a mistake, we just see a broken device and we think, oh, I'm going to make thicker braid, bigger wire, bigger jacket. When it goes wrong for the people using these devices, they quite literally fill up a graveyard of experiences of how this went wrong and either not use that device ever again or try to find better ways of using it. But in the long term, if you are using a device a couple of times and it's causing harm, you just avoid using that device and any devices coming from that company.
Yeah, so that was a lot of information. So you went into like the different options that we have for manufacturing. So what you focused on was reel-to-reel production, which is basically continuous production of catheters. So you have either dip coating or you have the possibility of extruding onto a reel, which is basically nothing else than the replacement of your mandrel. So the point would be that this mandrel would be having the possibility of removing the catheter at the end. Is that correct? And it has to be flexible in some way.
And typically you stretch that mandrel. So when you stretch it, you make it thinner and then it doesn't get automatically reused. Potentially, if we found a reel-to-reel mandrel that has lubricious coating enough to the point that we can just slide it out and actually just reuse that full mandrel again, that would be amazing. Not exactly there yet, but I do know of technologies coming out that could alleviate themselves of that.
What kind of materials are usually used for this reel?
POM, silicon, acetyl, PEEK can be used. You have to get high temperature materials. Just as it's going through that extruder, it could be 200, 250 degrees that it might be seen.
Okay. Very interesting application. I would have to think what the best material would be that just barely has the technical capabilities, but is not too expensive and not too environmentally taxing. But the possibility of recycling that afterwards is pretty high. And you could also be thinking of, oh, is this possible to be reused? Because if it holds its shape, it's going to be fine to reuse again. And then you went on to, okay, how do we do the braiding on the reel, and then how do we cut the specific braid to length, and then we can also have co-extrusion with different durometers, which is extremely interesting. So you would not have to like stitch different durometers together, but you can have continuous, let's say, changing of durometers or stiffnesses, which is extremely interesting. How would you change the material selection in this? You would try to go for something like an ultra high molecular weight HDPE, of course, for the liner, so that you have the lubriciousness. What in terms of durometer, is this significantly stiffer than PTFE, or how does it look like?
Tensile strength, it can be like 6 to 15 times stronger than stainless steel. So it is a wonder material. As for durometer, it is high, but if we can make it thin enough, we get around that.
Yeah, you only get that strength if you orient it properly. So if it's not oriented ultra high molecular weight HDPE, then of course it's not going to have the strength. If you orient it, it's actually a very, very high stiffness, high strength material. So there are different, I think it is rope application that is using ultra high molecular weight polyethylene that is oriented. So you just pull on the chains, which is extremely efficient way of distributing the mechanical force. If it's not oriented, you'll be very close to what HDPE can do. So like the 30 megapascals ish. But PTFE isn't as strong either. So, and then, for the braiding, what kind of material would you use? Just steel?
Stainless steel, 304, LVM, LV, they tend to be the most common material because it's strong and it's cheap. So 316 a little bit more expensive. Nitinols, titaniums, unrealistic to be putting into each single device.
Yeah. What do you think of peak braiding?
It's not as strong as stainless steel, and the cost at the moment would be higher than if you were doing stainless steel. Very on board with it, but I do envision the idea too of this isn't just how we make the device, but how is the device recycled after its use? And in an ideal world, I would love if you could melt at certain temperatures and be able to separate the polymers, the metals, or whether it's chemical, whether it's heat. And then I also have a thing where I know these devices, these single-use devices, are single-use in developed countries that have the luxury of doing it. But these could be used 20, 30, 50 times in countries who do not have, cannot afford that. So in my head, it's if we can design it well using the same materials but in a different way so that it is reusable and lends itself to both sides without adding any more cost or having any effect on the sustainability or the carbon footprint.
Yeah, I mean, recyclability, especially mechanical recyclability for such a complex device with multiple layers that have different functions, is going to be extremely difficult because you would need to be able to separate the layers and then to separate the layers into volumes that are economically viable, which is extremely difficult to say, especially if you have specialties like PEBAX and specialties like ultra high molecular weight polyethylene, which is anyways pretty difficult to melt anyways. So in that case,
what if our outside polymer was the same as our inside polymer? If we were able to dial it down so we have polymer, different durometers from whatever we do to it, and metal. And we just have those two sides, and that's all we're trying to separate in recycling.
Are you a medtech company and you want to make your device more sustainable, but you're not really sure how? With the link in the description, you can now book your free consultation. Click the link, find a time that suits you, and show up with your questions. We're here to help. That would probably work. You would have to shred it, and then you have to do melt filtration so that you get rid of the metal. It's definitely more feasible than if you have a different mix of polymers. And then in the end, it's also the question like, do you want to go for something like a mechanical recycling? Do you want to go for a solvent-based recycling, or do you want to go for a chemical recycling? And then there's also the discussion that you indicated is, wouldn't it make sense to make this multi-use? And we have had Ulrike Marchak on, which is from Vanguard. It's like a company that does remanufacturing of single-use medical devices. And it's very much possible to do so with devices that are labeled single-use, to clean them, test them, make them fit for medical use again, and then bring them onto the market under the name of Vanguard as the legal manufacturer. That is going to be still a single-use device then. So it's just like the company takes used single-use devices, or used single-use devices which are declared as waste, and transforms them into new single-use devices. So it's not I take plastic, I take steel, I take mandrel, I take PTFE, and then make my catheter, but I take old catheter and make new catheter out of that. This is a very simplistic way of putting it, and that works. They still have a certain amount of scrap that they're having to throw away, of course, but it's definitely a thing. And then, it's the single-use versus multi-use discussion is not that simple, because it's also about the workflow, the simplicity in the hospital. And as we have like seen it, and you have said that before, engineers don't tend to go to hospitals. They don't tend to understand the clinical very well. And this is, I think, one of the key challenges of the industry overall. It's like that engineers don't tend to talk to clinicians, and the other way around. Because, the workflow is extremely important, and the reprocessing units are difficult to maintain. They have to have a quality system. They have to have a dedicated person doing this. And then you have to find the people with the skill. So it is not that easy of a discussion. Okay, but sticking with material and recyclability, so what kind of materials would you aim for if it's not ultra high molecular weight HDPE? What kind of materials would be alternatives?
That is one of the options. The other one is, like we said, if we have HTP or UMFI on the inside and UMFI on the outside, we could do it even with PEBAX on the inside and PEBAX on the outside. So there is bio-based versions of PEBAX out there from the likes of Arkema, and you can even get the likes of Dynaflex have lubricant additives that can be added to it, so it can resemble that lubricity. May not have the abrasion resistance that PTFE has, but again, pick the option or pick the side that lends itself to your application. So nylon-based materials, polyurethane-based materials, polyethylene-based materials, they tend to be the ones that I know we can use today.
Okay. So if you don't have the base polymer have the lubricous properties, you will find an additive that basically does that. So you would go for something like a thermoplastic elastomer, like PEBAX, which is a polyamide-based thermoplastic elastomer, or thermoplastic elastomer based on polyurethanes, and then use additives to get the lubriciousness that you need in order to have the liner. And have you seen that in action, or is that just like proof of principle?
Yes, that's an action. So it does take a number of years before a device comes to market. It could take 2 to 4 years before that device is out in the market and used in patients. And I believe it has been the end of last year was when end of last year or beginning of this year was when the first device in the market came out with that Dynaflex technology that I have experimented with before. So it is a completely viable solution today. And then there's another point that you said there where it's like that the engineers are designing these a little bit in isolation. So I'm co-collaborating at a workshop with a hospital and research center in New York, the Jacobs Institute. And yesterday I spoke to an absolute incredible man, Dr. Ken Schneider, and he was telling me about what goes wrong in the devices, what he has seen when they're misused. And to be honest, I was walking around like a ghost for 6 hours after it, and then broke down in tears for a half an hour because of the guilt and naivety that I had around how I was being designing these in isolation, or talking to a few clinicians that were telling me what they wanted to hear, but they weren't going to get therapeutical on me and break down to what it was. But he was saying, like, there's one aspect of a device. Many devices have this point, which we call the point of no return. So it's when you're releasing a stent or a valve into the body, it's that point where when you remove it so much that you can't get it back in. And in our IFU, we say you wait until all these things are checked and everything goes well. So you could release that stent. And then he said about how potentially the wall of that artery or vein was so thin that releasing it fully ended up ripping it. And you have 1 minute to try and keep this person alive. And he said, no company has ever designed a system on what you do if this happens. It has been entirely ignored because us engineers do not actually get to talk and meet with the surgeons to see what their real life experiences is. Because for us, if this breaks, if I bend and twist and damage this catheter, and it actually healed itself very well, I do what I call trauma-based learning. I was like, oh, that broke. I know I'm going to fix it. I'm going to make the braid stronger. When that happens in a clinician's or a surgeon's life, it's a whole different thing that they're bringing home with them that night. So designing it for optimal use and not just because of the materials working well or you meeting your cost of goods. And the first step to that is getting a more intelligent, more advanced manufacturing process.
And it's like what I hear so much is, oh, we don't do that sustainability stuff here because like we put our devices are putting the lives on the line. And I completely get that. Safety and performance is number one, number two, and number three priority. But that doesn't mean that sustainability is not possible. Or, what's your take on this?
They should not be exclusive. It shouldn't be sustainability is like a bad word that you hear around the place that I think it's going to make life more expensive, more difficult for you. It's a it's a development, it's R&D, it's looking around and seeing what the other options are, being curious about it, seeing is there a material, is there a bio-based material, is there a company that is close enough to us that could start into bio-based materials if we integrate with them early and they go developing it. So we might not have it for this generation, but we could have a cheaper solution the next generation by having the discussions today.
Yeah, and I mean, what I would also add to that question is, sustainability is usually perceived as a premium. Oh, it's going to be more sustainable. Let's do the right thing, but it's going to be more costly, and nobody's going to pay for that, so we're not going to do it. What's your take on that? If we implement all the measures that you suggested here, like taking a more sustainable liner, then going ahead and improving the manufacturing method, and doing a reel-to-reel manufacturing, continuous manufacturing, what would that cost or would that make the device extremely expensive, or what does it do to the cost?
I'll answer the first question first of all. What's my opinion of it? So, as humans, have we not yet learned that this instant gratification of getting something now never works out in the long term? So by putting the efforts into the sustainable practices now, it means that you're not shipping materials from halfway around the world to get them here. You can actually start developing the sustainable bio-based materials here rather than abroad. So doing that now is by far going to be sustainable all around the life cycle of the product, where it gets disposed of, how it gets disposed, if it can get recycled. There's so many elements where this makes it cheaper, but it is going back to put in the work now so you can get the rewards later. It's not going to cost you more money because the reality is it will be cheaper if you were thinking about all these different aspects of it. For everyone, as an entire ecosystem, it would be cheaper if sustainability was front in line. Not front in line, but a standard necessity and requirement.
Yeah. So what I'm going to do now is I'm going to play devil's advocate a little bit, and I'm trying to like poke holes at your theory, because it's like if Nietzsche called this philosophizing with a hammer. If I can't disprove it, it's probably true. So number one, let's start with you mentioned in the beginning that there's like 7,500 different applications of the catheters. And if you have a big investment in terms of facilities and in terms of production technology, that's not going to be cheap. So you'd have to have a lot of capital expense upfront. So you do invest in production technology. And then that production technology, how flexible is it in terms of customization at the end? So do I get the economy of scale out of this? And do I need to like reduce the amount of different catheters that I'm going to make?
So your initial investment is going to be remarkably higher compared to those R&D teams who had very little money that ended up creating the devices just like this. So your initial investment is going to be much higher, but then you are building medical devices at 20-25% the cost of what you're currently doing it today. And that is me saying a very safe number. You can do it much cheaper than that. It'll essentially be the materials and the electricity and the upkeep of the machines. So by putting that time into a more sustainable solution, you are walking out and you'll be able to make 5 times the devices for the same price once you have manufacturing up and running. And then, yes, you can build a platform device that it just changes the length or changes the shape on the other end, or builds a blank that you can use for multiple different applications. So you can bundle up all those different applications. So you're not building 7,500 different devices. You are building realistically probably around 400 maximum different devices and platforming them into the different applications.
So it is still customizable in the end.
Absolutely, entirely.
Then the second thing is, okay, but I am a small company now. I do not have too much money. I just want to do quick and dirty, go to the market, prove that my clinical works, and then figure out the nitty-gritty stuff later. So at one point does it make sense to invest in this manufacturing technology?
So if you're a small company and your initial intention is to get acquired, you would end up probably you'd be go for a contract manufacturer. You'd build it at the standard way you're doing it, get acquired. Then the larger companies will take that and make the next generation of it, and they would do it in a more sustainable way. So as a small company, you may not do it yourself, but there's contract manufacturers out there around the world who already have these processes set up. So you don't have to reinvent the wheel. You don't have to create this from scratch. You just have to work with someone who knows this types of processing.
Okay, so you would then recommend to work with industry leaders that are already implementing these reel-to-reel continuous processing of or continuous manufacturing of catheters. That is what your advice would be.
Yes, so it doesn't have to be a case of I'm too small to get into this. It's just that you have to go and find someone who can fill in the gaps that you can't do, which is the standard practice of manufacturing, anyways.
So yeah, what is there left to discuss? We've talked about materials, we've talked about processing, we've talked about design. How can we design it differently? We talked about the sustainability piece, the cost piece. So it all makes sense in a way. So why is the industry not moving in that direction? Or is it just moving in that direction extremely slowly and we can't observe it?
The industry has moved in that direction. Like what I'm saying is not something that's out of the back of my mind. It's something that has been tried and practiced by a series of companies who had sustainability in the forefront, and it was a big driver for them. And they have, from doing it in a very unique way, being able to supersede all their competitors on entry, and their competitors can get nowhere near their cost prices because they're still doing it the traditional way. So this has been done. It's just if you've been doing it some way for 30 years, why would you change? And you keep building devices that way.
Yeah, so it's the good old we've always done it like this and it still works.
Yes.
Okay. What percentage of the industry would you say are on the traditional side, and which ones, and how much would be on the let's do it the new way, the efficient way?
So very limited in the US and Europe. We are doing it more along the traditional way. I think our cost of entry is a little bit higher versus what you might find over in Asia. But even the prices that the government have set out for in China for what a device must cost, it would be impossible to build it the traditional way. So I've seen a lot more places in Asia that have adopted this style of manufacturing versus what's done in Europe or the US. So it is only a small percentage that are down to this level because one, lack of understanding, lack of education. It's like they don't know that this is possible. They, as I said, the process engineers, they increment on what the R&D engineers gave them, and it's not their job to suggest a different type of material. It's their job to make this process better and faster. and safer.
Yeah, and there's also, I'd say, the cultural aspect of it. We've always done it like this. This is a tried and proven material. We have it through clinical, or we are in the regulatory approval, so we're not going to change anything. And just, oh, my favorite one is, it's compliant, don't fix it. So I really love this one. You just admitted it's in need of fixing, and you still won't do it. I think this is the cultural change that we need to make happen. We need to bring back the spirit of innovation. It's like, I think you do a very good job of spreading that, but it's usually also all about incentives and about telling a good story, and telling a good story of why it makes sense. And what's your take on this?
We have quite a beautiful planet that we live in. It's not immortal. I think it is quite insane as a species that we cause so much harm and disruption to it. Like we talk about environmentalism and sustainability like it's a discussion that we could have and often sway against it. Like that is psychopathic insanity to believe that environmentalism is just a discussion point. Like it should be a standard norm. There's a finite life to finite resources to everything that we can use. Unfortunately, there are a series of people on the planet that are looking to make that better, but it does stress me out endlessly that it's still a discussion that we can have two different opposing opinions on rather than agree sustainability and recycling and environmentalism is a standard and just maybe have disagreements on how exactly we do it. So that's my side of it.
The point is the topic is also convoluted and complicated and difficult. And I just had a discussion with Matthew Yamatin, and like he says it, or he has this example of the shampoo bottle in the supermarket. So you go to supermarket, you're willing to do something that is good for the planet, and then you see like 15 different labels. So this one is more concentrated. This one is recyclable. This one has 15% 15% recycling content in it. And this one is bio-based, and this one is whatever, biodegradable or whatever. And then people are so confused on what actually is better that they just stick with the one that they always have done. And as if you do not know the answer, sticking to what you can is a strategy that people usually employ. If you're confused about what is the right answer, you stick with the one with the devil you know. And that is, you have to cut humans some slack also. Economic and social aspects are important too. Like the same thing with single use versus multi-use. Cost is a thing. If you can't afford it, and we have like the healthcare system also that are under heavy financial stress, so you can't afford to make it like 2 times, 3 times more expensive, your device. So if there is a sustainable solution, I call it in air quotes, that is more ecological but costs twice as much, is not actually sustainable. And I really am fighting for to bring the original meaning of the word sustainability back, because sustainability used to mean like to be carried on into the future without detriment, meaning that this is not only from an ecological perspective, which we're not doing too great at, but also from a profitability perspective, and also from a socialist perspective. We don't want ruptured arteries just because we took a material that is a little bit better for the environment or a little bit better for our wallet. Safety and performance is number one in healthcare. And I think what I see too much is use that as an excuse, because change is so much pain. And we need to, I think, employ the tools that we get in modern history or the most recent years, like AI, like documentation, like new development methodologies, like the lean startup methodology, to increase the speed of innovation and speed of change, so that we are actually able to change the products in a better way, and not make them only better for the environment, but also better in terms of costs. Like you laid out, it's like like a quarter of the cost, or order of magnitude better in terms of cost. And there is where you actually can like sneak in the vegetables with the pasta. you know?
And better performance.
Yes.
So with that way of doing it, you are not manually hand to hand overviewing these each individual processes or connecting two tubes together that might break apart really easily. This is all continuous and flowed. It is a much safer device, much more reusable. So there's an interesting argument I had once upon a time here in Ireland about windmills. And I was all for windmills, completely for them. And I had a discussion with a man who said, no, they're not sustainable. They cost this much to get, and when you put them up, and it takes this many years for them to come back, but they break before that, and you have to replace them. So it doesn't work for cost. And I had to go figure out what he was talking about, and then I realized we are buying all our windmills in from France. So if you're buying them from France, shipping them all the way over to Ireland, and it's taking months to actually get them all the way over, and you're doing it by truck, and you could be going 50 kilometers an hour bringing it around, of course it's not sustainable. But if we had such a high demand for windmills, we would build them here in Ireland. They would then be cheaper, you wouldn't be costing as much on transport, and we'd have an ability to fix them more locally, and then it gets more sustainable. So, yes, he was right. They are more expensive than just using fossil fuels if you kept doing them that way. And as the medtech industry, if we keep doing stuff this way, of course, that automated manufacturing route is going to be more expensive to get into it. It always will be. But once you start into it, everything from that point on is cheaper, more effective, and better quality.
Yeah. Okay. Damian, let's come to the last question. What advice would you like to give to teams that are starting out to build a catheter? What advice would you like to give them?
I think curiosity. I think curiosity is one of the best superpowers we have. Just asking questions, like the reason we got in contact first is you're an expert in sustainability. So I had 100 stupid questions to ask you so that I can understand what the hell sustainability means. Is it mean that I'm recycling my cardboard box and using on the outside? Or from having these discussions, that's how I've grown and learned about these different ways to even use the same polymer on the inside and the outside. I didn't realize what a concern that is when it comes to recycling. And I've seen with companies where they think sustainability is changing something to do with the device itself. Sustainability could be simplifying your packaging. It could be using a more realistic local source that ends up being cheaper. And rather than getting these highly branded, highly marketed things that have this beautiful user interaction, you could get the cheap cardboard box again, and you're better for the planet, and it's cheaper than these highly branded packaging solutions. So it's just finding out what is sustainability for you, not what it is in environment. It's like ask questions related to what can I do or what are other companies doing that is going down that road, and then make your decision yourself on whether this is cheaper, more expensive, or else at least have it in your back of your mind so you can plan it for when it does become more cost effective.
Yeah. And I think also it's not dismissing the small steps that you're doing towards the solution. It's like, oh, it doesn't really matter if I do it. Like a small step gets you in the right direction. Maybe you're not up the mountain yet, but like every step counts.
And like sustainability with, say, Umfi, I don't know. I knew Umfi for a while, but I don't know what I have known ultra high molecular weight polyethylene to the same degree I have if I wasn't initially curious about sustainability and it led me down to find new materials. So, same thing. We've been using a lot of the same materials for a long time. Sustainability could be the excuse to go out and see what other materials are out there that might actually be better for the application we're trying to use it for.
I am very much subscribed to the idea that sustainability and innovation will go hand in hand together. I think innovation is about making the product better, and sustainability is also about making the product better. So they have the same goal, and I think they will work very well in tandem. Good. So Damien, do you have any last words?
No, just a little bit to that last point of innovation isn't, if sustainability isn't focused within innovation, innovation will not be sustainable.
Yes, it's very good.
So, no, absolutely loved having this conversation, loved going down through it, learning even myself and challenging myself on how I would do that today for local companies rather than companies who have all that behind it. So, what an incredible podcast. Really enjoyed it, Lucas.
Good. So Damien, how can people reach you?
So through our website, eyedea.ie, EYEDEA, because I'm dyslexic, so I'm going to make everyone else suffer with my spelling mistakes. And we are having our opening of our new facility is coming up on September 18th. So I'm very, very excited. That should be just around the corner now, where we will actually be able to bring people to this 100-year-old facility that we have that will be converted into a space, helping to build devices for the future.
Okay.
And LinkedIn. LinkedIn's always a good place.
Very good, very good. So thank you very much for watching. This was Damian Carr from Eyedea MedTech Education. And until the next time. I hope you enjoyed this episode, and if you did, share it with someone who can derive value from it. And let us know in the comments if you enjoyed it. If you still have questions, use the link in the description to book your free consultation. Click the link, find the time that suits you, and show up with your questions. We're here to help. Thank you very much for watching, and until the next time.